So in this video, we're going to be talking about something that we've touched on a little bit in other videos and in class. But today we're going to be talking about the antiderivative and something called the indefinite integral. So when we've looked at integrals so far, we've always looked at integrals with limits right up here and up here. And it turns out that when we get those limits, that's called a definite integral. And an indefinite integral is when we don't have those limits right here. Now, a definite integral, remember, is a way that we can think about getting an exact area under the curve between an interval, or it gives a net change between an interval. So really, it gives us a number. What an indefinite integral gives us is a function. And what we notice is that function is consistent of the antiderivative, which is that function capital F of x, which we've talked about before. And this c is just a constant. It's a constant that comes out of the integration. Don't worry about this little vertical line right here. That was actually just a cursor that was there when I took a screenshot. It means absolutely nothing related to mathematics. But you might be asking, okay, why does that constant show up there? Well, remember that the fundamental theorem of calculus tells us that if we take the derivative of an antiderivative, we just get the function back. So when we take the derivative of this antiderivative right here, it wouldn't matter if we included that c or not, because when we take the derivative of a constant is always 0. So let's give an example of this, okay? Let's say we had an antiderivative that was given by 2x plus 1. That means that the function itself would be given just by 2x, okay? So, I'm sorry, not 2x, just 2. Add a little x sneak in there. So let's say we worked on this backwards, okay? If we took the integral of just 2, what we would get that would come out of that would just be 2x. But we wouldn't get that constant that showed up there. That's why we need to put this plus c. Anytime we evaluate an indefinite integral, we always have to add that c there to take into account that constant that comes out. It's just something that you should always do every single time you evaluate an indefinite integral. So here's some examples of some indefinite integrals, okay? So right here, we have the power rule in reverse. Notice it does not work for n equals -1. So for example, if we have the integral 1 over x, that doesn't use the power rule. We actually see that down here, and that's where we get a natural logarithm. But we'll get back to that in a second. So anyway, here's the power rule. So for example, if we use the power rule, the integral of x squared dx is going to give us 1/3 x cubed plus c. Now, how can we check that our antiderivatives, or what we put in a definite integral, is correct? Well, again, by the fundamental theorem of calculus, this is capital F of x plus c. If we take the derivative of that indefinite integral, we should just get the function. And as we can tell, if we take the derivative of 1/3 x cubed, we end up with just x squared. That's just applying the power rule to a derivative. So you see it works. And this is always a very good check. You can always do this to make sure that the antiderivatives you're calculating or the solutions to indefinite integrals are indeed the correct solutions. Just take the derivative of them and make sure you get what was originally in the integral in the first place. That's always a check you can do to make sure you've done it correctly. In my mind, that's one way that evaluating integrals is somewhat easier than evaluating derivatives. You have that check in place that you can do. Now, technically, you could do that check by doing an antiderivative when you follow or when you do a derivative. But when we were learning derivatives back in the previous semester, we didn't have any tricks like that. So just keep that trick in mind. It's really useful. All right. So let's look. Let's get that big. So let's erase all this, and let's look at a specific problem that you guys can try out yourself. And this is going to work very much, very similar to that introduction to derivatives video I showed. We have all of these indefinite integrals down here, and you're going to have to use some of those to evaluate various indefinite integrals. I guess the one that we can't quite see is if we scroll down just a teeny bit, this one down here, the indefinite integral of e to the x is just e to the x plus c, so in case you couldn't see that one very clearly. All right, so let's look at an example problem. All right, so try to evaluate this indefinite integral on your own. Pause the video. Okay, so if you try this one, first of all, we look down at this one right here. we're going to look at the derivative of sine. Notice we have a 2 out in front. Remember, with derivatives, with limits, with integrals, if we just have a constant out in front, that constant just stays there throughout the entire integration or taking a derivative or whatever you're going to do. So this will end up being negative 2 cosine x. And then when we want to take the derivative of cosine, we just look at this. The derivative of cosine is just sine. So then here we have minus sine of x plus c. Now some people might be asking, why did I only add one c to the end of it? Wasn't I doing two different integrals? Well, yeah, if you split these integrals up, yeah, you're going to have two different c's, but a constant plus a constant is just another constant. So whenever you do an indefinite integral, you shouldn't be having multiple constants floating around. You should always just have one whenever you solve an indefinite integral. All right, so again, if you didn't quite get this one or you're unsure about what integral properties we were using, pause the video, try to go back and do it again. If you were able to do this one okay, then let's go on to another one. All right, so try to give this one a shot. Pause the video. Okay, so the first thing you'll notice is that these first two sections are going to be utilizing the power rule, and this last one is going to be using the integral of e to the x down here, which I will scroll down so you can see that a little bit better. All right, so by using the power rule, this first one is just going to be 1 over 2/3 plus 1 t to the 2/3 plus 1 minus, remember, square root of t is the same as t to the 1/2. So this will just be 1 over 1/2 plus 1 t to the 1/2 plus 1, and then e to the t, there's a 3 out in front of it, but again, we don't really care about that 3, it's just a constant, it'll stay there. So we'll have plus 3 e to the t, so that one doesn't even really change. So if we rearrange this, we should get that this simplifies to 3/5 t to the 5/3 minus 2, 2/3. Yeah. Wow, I just had a major brain fart right there. I'm sorry. 2/3 t to the 3/2 plus 3e to the t, and we have to add our plus c there. So sorry, ran out of a little bit of room. But if you do this whole indefinite integral, you are going to end up with that. So if you have some questions, where did the 3/5 and the 5/3 and all that stuff comes from? Remember, this is just adding fractions together. 2/3 plus 1 is the same as 2/3 plus 3/3 or 5/3. Now, since that's on the bottom, we can flip those. So instead of 1 over 5/3, that's the same as just 3 over 5. So you got to remember to do fractional stuff like that when you're doing these power rule examples with indefinite integrals. All right, let's see if you guys got one more in you. All right, try to give this one a shot. Pause the video. So if you're stuck already on this one, you don't really know what to do, keep in mind, I'm not going to give you something you don't know how to do already, okay? Have we learned any kind of product rule for antiderivatives? No, we haven't, okay? So you shouldn't be expecting to do something like that. However, I can rewrite this integral. If I multiply that r squared through, this will end up being r to the -1 minus r squared plus, remember, the cube root of r is the same as r to the 1/3. So this will then become r to the 7/3 dr. All right, so now if you didn't get to that simplification, try to do it again. Give it another shot. All right, well, if you look at this one, you'll see this first part of the integral, well, that's related to the natural log. You'll notice with this natural log antiderivative, we have an absolute value of x. So you always got to put that there whenever you're evaluating the antiderivative of 1 over x. However, there are some cases where your domain of x makes it so you're never going to have to use that absolute value. Sometimes on AP multiple choice problems, they don't include that absolute value. Sometimes they do. Usually they include it or don't include it based upon the domain of the function you're looking for. So just keep that in mind. You just want to pay attention to that. So anyway, the integral of this first term will be natural log of the absolute value of r. The second one will just be the power rule, so that will be minus 1/3 r cubed. And then the last one will again just be the power rule, and without talking about the adding fractions sort of things that we that we did in the previous slide. I'm just going to tell you this one will end up being 3/10 r to the 10 thirds, and then we have to add r plus c to the end of it. Again, I apologize for running out of room. But anyway, this is what you get. So this is a basic introduction to how to solve antiderivatives. I would suggest going back in this video and re-watching this if you're having any issues. If you'd like some more practice, this is where your book is an incredibly good resource for practice. If you just go to, I believe it is chapter 5.3, or is it 4.3? No, actually, I think it's 4.3. Anyway, ask me in class. I don't have my book on me right now while I'm making this video, but I can certainly in class point out several example problems you guys can do in the book if you want to get some more practice with this. Other than that, we will talk about a little bit more complicated versions of these simple antiderivatives in the next slide, an example of how to solve those.